All right, as we are heading to the last week, we will have 3 lectures, a chapter each time. We will have a lab today and a lab tomorrow, and that the Tuesday lab will be the last lab that we will have. And we will finish up the course with a exam just on the last section. As we turn our attention to the last section of the course, the title of the course is Earth and what? Space. And so we're going to turn our attention to space. And we're going to take 3 stabs at looking at space. We're going to look at things that are relatively close to us, and so that will encompass the solar system. And a lot of times that is taught very thoroughly in elementary school. Then we're going to look at things that are a little bit farther away, but not too far. And so what we're going to do is we're going to look at what is in our galaxy. And our galaxy is called the Milky Way, so we'll look at what's in the Milky Way and how we study what is there. And then we will, in the last chapter, we're going to look at what's beyond the Milky Way to the edges of the universe. And so there's some pretty strange things that are way out there, and we're going to describe some of them and kind of give some ideas about what that might look like. And so this particular photo was taken in South America. What constellation do you see? The Big Dipper. And so low on the horizon, reflected into the very still lake. And so wonderful picture, but very focused, and the constellation is seen fairly well. Moving into space. Now, the solar system. We, in modern day, know a lot less as a collective group of people about the night sky than people in the past. Okay? We relatively know little, the average person. And the reason really is when you walk outside, let's say you're in the SMC until late at night and you walk out here and you look up at the night sky, how many stars do you see? Not a lot, almost none. We live in a society and a time in which there is a lot of light that is produced at night, especially around our cities. And so we get a lot of what's called light pollution, in which the ability for us to see the stars is much less there than what has happened in the past. In the past, when it became dark, there was basically nothing to do. There was very little light, and so the stars dominated the night sky. And so a lot of people spent a lot of time looking up at the night sky. And quite frankly, some people worshiped the night sky, unfortunately, but they actually paid attention because that was there and they couldn't get away from it. If ever you've been out on the ocean on a cruise, or maybe camping in the desert or driving overnight in very unpopulated areas, you might look up in the night sky and be surprised about how many stars there actually are. Now, our idea of the solar system and what was around us was kind of known up to a point and really well described up to about 1609, when the development of the telescope came about. We understood that there were a lot of stars in the sky, and we believed that there were only 5 planets, because with the naked eye, what we could see 5 what looked like, or could be mistaken as, very bright stars were in the night sky, but they traveled along the night sky in a different path than the stars, so we separated them and called them planets. The original name for planets is derived from a word that meant wanderer. All the stars seem to be relatively constant in relationship to each other, except for these 5 things, which went around the night sky in a different pattern, and so we called them planets. Now, this is a really interesting photo in that the there are 4 of the planets that can be seen with a naked eye are visible at one time in the early evening, and this was in July 2010. And so we've got Mercury, Venus, Mars, and Saturn all in the night sky, and a few of the brighter stars that are seen. And so at some moment in time, you might even mistake one of these entities for a star, but they behave differently. We now know that we have classified 8 planets and a host of what a lot of people, or what a lot of texts call satellites, we call them moons, are around planets, and then a whole bunch of other stuff that is in our solar system. And we'll talk about some of what the other stuff are. If by chance you pick up a book about astronomy or Earth and space science, depending upon what year the book was written, it will say either 8 or how many planets? 9. We're going to talk about Pluto and what happened to Pluto and its demotion from planet status. So we'll talk about that a little bit. This is not to scale, but when we look at the solar system, we have 8 planets, and they can be divided into 2 major groups. If you look at the picture, where is the dividing line between what and what? Which planet? Between Mars and Jupiter. There is something fundamentally different about how they're shaped and what they're made up of in the first 4 planets and the last 4 planets. And so we're going to see a lot of differences. And so we talk about the planets that are the inner planets, or the closest ones to the sun, and the outer planets, the ones that are further away from the sun. And obviously you can see size is a big difference. The ones that are outside are much, much larger. The ones on the inside are much, much smaller. And we'll talk about some other things that are differences between. We know the things that are in the solar system is the sun itself, and the sun is huge compared to the other planets. Satellites or moons, we know we have asteroids, comets, and another category called dwarf planets, which we'll get to at the end of this chapter. But really, just like the atom, where the sun would be representative of the nucleus and the planets be representative of the electrons, most of the space or the volume of the solar system is made up of absolutely nothing. And so if you look down at the smallest things that are made, it seems to be something in the center with things around, mostly space. And as we go out to something very large, our solar system, we're in that same pattern. It seems like a repeating cycle if you look from the smallest to the largest. Seems like someone kind of designed it to look all the same. Now, when people looked up at the stars, what you can observe if you spend a lot of time looking at the stars is that the stars tend to move across the sky over the period of the evening. Now, it's really hard to detect if you're looking at it because you got to stare at it for a very long time. But if you look up at the night sky and then you do something and then you look back up and you look for the stars, they've shifted over. And they continue to shift over throughout the night sky. Now, what was odd to people was that all the stars shifted at the same time. And so the distance between all the stars never changed. But the whole thing moved across the night sky. It actually moves at the same rate as the sun moves during the day. And so you know the sun arcs over the sky, but you don't watch it. But you look at one time, it's here. You look at another time, it's there. And you look at another time, and it's setting all of a sudden. And so it moves at the same speed. Now the planets, on the other hand, they did move across the night sky, but they moved at a faster or a slower pace than the stars. Most of the time they moved in the same direction as the stars went across the night sky, but every so often, over months, sometimes they were moving in the opposite direction of the stars. And what they did was, over time, if you actually recorded it, you made these little loops as it goes around the night sky, and they're kind of looping around. If you recorded the position of each of the planets as comparison to the stars that they are near. And so this retrograde motion, or it moving in the opposite direction of the stars, was something that was different. 5 of the planets did that, and so they were classified as something different. Now, at the time, people didn't know what they were. They actually thought they were also heavenly bodies that gave off light just like the stars. We now know they are planets that are not glowing at all, but they're reflecting the sunlight that hits them, just like the Earth absorbs some sun, but it also reflects. And so, relative to other places, we also can be seen in the night sky if you're on another planet. Although we haven't been to another planet, but we have been to the moon. Now, this retrograde motion occurs just by, it's more an optical illusion than the fact that they're moving in a different direction. It is because of how we are positioned as we go around the sun over a year, how or why we may perceive that the planets are going backwards. So what we're going to do is we're going to take a look at an example of Mars compared to Earth, and why Mars might look like it goes backwards at certain times during the year. Okay, so you can see that we both go around the sun. The Earth, because it's closer to the sun, goes faster. But when we look at the night sky, okay, we're going to see Mars every so often. Now, it all depends upon where we are relative. So if I look at Mars compared to the background, sometimes it looks like it's actually heading in the same direction as the stars are moving. But that's just relative to where we are. All of a sudden, as we pass it, to our eyes, compared to the rest of the stars, it looks like it's going backwards. It's not going backwards, it's just our relative to positions. And so, at times, it looks like it's going with all the others. Here is a collection of photos over a lot of days. And you can see the planet compared to the rest of the stars. And every night we take a picture, it looks like it's moving backwards. And then it looks like it's moving forwards. But this positioning and seeing this takes months. But you can see how they travel relative to the stars and the placement of where the planets are. Now, would you have the patience to start on 10/22/09 and finish at 5/15/10 to do that? Well, for us, if we can't see the next episode right after the last episode and binge the whole show, we're not going to watch, right? But way back when you didn't have a lot to do, being able to look at the night sky over long periods of time wasn't as boring. It was the thing to do at that moment in time. And so they were able to perceive this. Now, the idea about how everything moved are theories. And so there were lots of theories about how things moved in the night sky. And so one theory that held around for a very long time was the Ptolemaic idea, or the Ptolemaic System. In this, it was really personally just like a human. The Earth is the center of all things, okay? Very egocentric, and so that is the idea. The Earth is the center of the universe. The moon orbits the Earth. All of the planets orbit the Earth, but they orbit in little circles, so curlicues around. The sun goes around us in just an orbit. And then the stars were embedded in a crystal sphere, because they didn't move from each other, and that sphere was orbiting the Earth almost, but not quite, the same speed as the Earth was rotating. That's why they moved overnight. All right? Now, if you make a theory and you present this, what happens is, to prove your theory or to support it, what you do is you make predictions of what you would see in the future. And if your model predicts what you would see, that supports that model is good. And so for a lot of time, for a long time, the predictions that people would make based upon this idea actually came out 90 some odd percent of the time. 99% of the time, everything was exactly what they expected. So there was very little reason to go back and say, hey, something's not right here, okay? Based upon how they were taking data and based upon what they saw. Now, the idea of the Earth being the center of the universe was not just egocentric, but there was some rationale for that. The rationale being a lot of scientists were funded or were in actuality priests or monks that were supported by the church. And so everything that they were doing in science was to show God's handiwork and what's going on. And so when they interpret what they saw, they always interpreted it in context to how they understood Scripture. And how they understood Scripture was this, that when you read the Bible, he talks about the creation of us. So they assumed since God focused on us in the creation, then that must be the most important thing in the world, and that's where they got the assumption that we are the center of God's created universe. That seems to be a logical argument as seen through an interpretation of the Scripture. Okay? And so no one really questioned that for a very, very long time. And so this was referenced for over 1,000 years. That's a pretty long time to have an idea that was supported. Okay? But there were some anomalies. There were some things that didn't quite work out. And so Copernicus actually looked at that model and he said, okay, there are some errors. So how do we make this model better? Okay? And to change a model, you have two different ways you can do it. You can take a very simple model and then add exceptions and adjustments and calculations to adjust it to make it fit everything that you see. Okay? Those could get complex, and there may not be real good rationales of why to do that, but that's a way to fix it. Or you throw it away and you start off with another idea, and so which might fit the data better. And so Copernicus took on this problem, and what he found worked better was that, okay, let's put the sun as the center of the solar system. Let's put all of the planets rotating around the sun. The moon rotates around the earth. And if that were true, everything that you see in the night sky would work out, and most of the predictions are even better than the Ptolemaic idea. Now, Copernicus did a lot of work on this and didn't release it. Okay? He was afraid to release this information. And in actuality, most of his information wasn't released until after his death. But some of it did get out during his lifetime. And he was excommunicated from the church for this. The Catholic Church actually banned this idea and said it was heretical. And they had this in place until 1835, when they finally accepted the Copernicus idea as being the reality of the solar system. Now, again, the model worked, but there was some errors in it. And so the next developer that kind of tinkered with this idea that is credited is called Kepler. And Kepler said, all right, I like the idea that the sun is the center. I like the idea that the planets are revolving around the sun. But there was another problem. Again, it led back to people's interpretation of what God created. And so when God in the Bible describes that the creation was perfect and God created it perfect, then the idea that the orbits of the planets must be circles, because there was this idea that a circle is perfect, and if God made things perfect, it must be a circle. Now, defining a circle being perfect is a man-made concept, and they applied that God's creation of perfect must be this, but that's how both Ptolemy and Copernicus had the orbits. Kepler said, nah, it doesn't work so well. And so what he's going to be given is credit for making the planets orbit around the sun, not in circles, but in something called ellipses or ovals. And that actually made the data look a lot better. And so there are 3 laws that Kepler came about that mathematically fit a oval orbit better than a circle orbit. So these are the 3 Kepler's laws. Okay, so he made that idea. They're ovals rather than circles. But that idea is not going to just pass. What you have to do to a scientist is prove it with math. So he went back and showed 2 mathematical reasons why the ellipse idea was supported. His second law is going to talk about the apparent speed of Mars as it moves across the night sky. Sometimes Mars looked like it went very fast in the night sky, and sometimes it looked like it hit the brakes and slowed down. If it were a circle, it would always move at a constant speed, but if it's an ellipse, there is the ability to go fast, and there's an ability or a time period in which it goes slow. So the mathematics works out that the ellipses are much better. Let's take a look at that. The third law was that if by chance the orbits of the planets are in ellipses, then mathematically it can be converted into an equation where the period of a planet, or the time it takes to go around the sun, divided by how far away it is from the sun in distance, and if you cube that, you take the top and the bottom and you divide it, it all comes out the same numerical value for every planet. The units that you have to have are years for the period, how long it takes to go around the sun, and then what's called astronomical units, which are the distance from the sun. We use the Earth to the sun as a value of 1, and everything is either bigger than 1 or smaller than 1 if you're closer or farther away. We'll watch a little bit of this, but not all of it, because this becomes very mathematical also, which is not what I necessarily want you to understand from it. Well, and that's all I wanted you to know from that. So that was interesting. If we take the known values now of how many years it takes to go around the sun for each planet and how far away it is, all of them come out to the same numerical value, or you can set the period squared equals to the average orbit cubed, and those 2 values are the same. And so he put it out there, he said it's going to be this, and then he took enough data and showed all the calculations so that no one can question it. It actually mathematically works that way. And so we could take this data set for all of the planets, and we can look at the distance from the sun And so we say the value of 1 is the reference point. Some are closer, and some are much farther away. And then how many years it takes, although we would have to convert days into years. How many days are in a year? 365, okay. And these values are in years. We could actually set up mathematically and prove that. I don't want to get out a calculator, but if we did, it would.